Last episode, we built the density matrix, and it left us with a warning. The off-diagonal entries, the coherences, are the fragile part. Here is why. A real qubit is never truly alone. It sits in a world of stray fields and vibrations and passing photons, and it cannot help but entangle, gently and continuously, with all of it. We saw in episode 2 what entanglement does, and in episode 7, what happens when you look at only one half of an entangled pair. The half you keep goes mixed. Decoherence is exactly that, happening on its own, all the time. The environment is measuring your qubit whether you want it to or not. And as it does, the phase relationships that made the qubit more than a coin quietly leak away.
If the qubit is always leaking into everything around it, how does the machine ever compute at all?
Because it is a race. There are two ways a qubit decays, and the hardware people time both of them. The first is energy loss. An excited qubit relaxes back down to its ground state, and the population you carefully prepared just bleeds away. The second is subtler and, for us, deadlier. It costs no energy at all. The odds of each outcome stay frozen, but the coherence, that off-diagonal, shrinks toward zero. The qubit keeps its probabilities and loses its quantumness. Both decays are exponential, so every circuit has a clock ticking against it. Finish before the qubit forgets what it was doing, or you compute nothing.
So protect it the way I protect a file. Keep 3 copies of the qubit, and if one goes bad, take the majority vote.
That is exactly the classical trick, and it runs straight into 2 walls that do not exist for an ordinary bit. The first is the no-cloning theorem. There is simply no operation, none at all, that takes an unknown qubit and makes an independent copy of it. The linearity of the whole theory forbids it. So the very first step of the classical plan, make 3 copies, is off the table before you even begin. The second wall is worse. Even if you somehow had copies, the classical scheme wants to look at each one and compare them. But looking at a qubit collapses it. The instant you read the superposition you are trying to protect, you destroy the very thing you were guarding. So we need something stranger than backup. A way to store 1 qubit's worth of information across several qubits without copying it, and a way to find an error without ever reading the data. Remarkably, both turn out to be possible. Here is the move. Take a logical qubit, some superposition of the 2 states. With amplitudes we will call the symbol A and the symbol B. We spread it across 3 physical qubits like this. The piece that was the all zeros state becomes all 3 qubits 0, and the piece that was the all 1 state becomes all 3 qubits 1. Nothing in between. Only all zeros or all ones carries any amplitude at all. It looks like we copied the qubit 3 times, but look closer. The symbol A and the symbol B each appear exactly once, out front. They were never duplicated and never read. We build it with 2 controlled NOT gates, entangling 2 fresh qubits onto the first. The 3 of them now hold 1 logical qubit as a single, inseparable whole. Here is the encoder in real code, a handful of lines that turn 2 amplitudes into an entangled trio.
But if I am forbidden to look, how could I ever tell that an error even happened?
That is the whole trick, and it is genuinely beautiful. Suppose a stray error flips the middle qubit. In both branches, that middle bit is now wrong. We need to learn which qubit flipped without learning anything about the symbol A or the symbol B, because asking about those would collapse the state we are protecting.
That sounds contradictory. How can any measurement tell you an error happened without disturbing the state at all?
Because not every question is equally nosy. We do not ask what the qubits are, we ask only whether they agree. Measure 2 parities. Do the first and second qubits match, and do the second and third match. In a healthy code state, all 3 qubits agree in both branches, all zeros or all ones. So a parity question gets the same answer from each branch and never touches the superposition between them. The measurement collapses only what it can distinguish, and these questions cannot distinguish the thing we are protecting. They reveal where the error sits, and nothing whatsoever about the logical state. Those two yes or no answers together are called the syndrome. Each single qubit flip produces its own distinct syndrome, a little fingerprint that points straight at the guilty qubit. Read the fingerprint, flip that one qubit back, reverse the encoding, and the logical qubit comes out untouched, its amplitudes exactly as they went in. We located the error and never once measured the data. That is quantum error correction.
What if two qubits flip at once?
Then this little code fails, honestly and predictably. Two flips produce a syndrome that accuses the one innocent qubit. The correction makes things worse, and the logical qubit flips. This is a distance 3 code. It fixes a single error and breaks on two. There is no magic here, just a code too small to tell one story from another. Real machines use far bigger codes, the surface code chief among them, that spend many physical qubits to protect a single logical one. And this is where the promise of the whole episode lands. Protecting one logical qubit well can cost hundreds, even thousands of physical ones. That is the steep price, and it is why building a real machine is so hard. But there is a theorem that makes the price worth paying, the threshold theorem. If your physical error rate sits below a certain fixed threshold, then scaling the code up drives the logical error rate down faster than the errors pile up. Get under the threshold, and a noisy machine can, in principle, compute reliably forever. That is the promise the entire field is built on. We have reached the end. 10 or so episodes ago, we claimed a qubit was nothing but a short array of complex numbers, and that everything mysterious about quantum computing was something you could watch happen inside that array. We have now cashed that claim in full. Superposition was just numbers adding, interference was just numbers canceling, entanglement was a vector that would not factor. And measurement, the thing at the very center of all of it, was one line. Square the magnitudes of the amplitudes and read off the probabilities. That line is the Born rule, and it is the most precisely confirmed number in all of science. But sit for a moment with what that number does and does not say. Picture a qubit weighted heavily toward one outcome, with only a thin sliver of amplitude on the other. Once in a great while, you measure the rare one. Was that outcome any less real than the common one? The run where it happened was a perfectly ordinary run. The qubit was just as definite afterward, the collapse just as complete. The measure told you how likely you were to land there. It said nothing about what it was like to be there. The amplitude is a weight, not a verdict. Follow the decoherence we watched today all the way out, and you arrive at the reading where the branch you did not see is not deleted, only put forever beyond your reach. Both outcomes stay in the wave function. You simply find yourself standing in one of them.
And a rare branch is still someone's entire world.
It is. That exact question, whether a branch of small amplitude is any less real for being rare, is the one my novel Multitudes, The Indifference of Measure, was written to live inside. We spent this whole series learning to compute that measure exactly, from a length to array and nothing more. The structure it describes has no opinion about which outcome you were hoping for. The one thing the equation never contained is the part we supply ourselves, to care which branch we are standing in and to be kind to the people standing there with us. The structure is indifferent, we are not. Thanks for building it with us. Now go build something of your own.